everyone and welcome back. This is Safa. In this video, we learn how to design and tune a PID controller in Simulink and observe how each part PI and D affect the system behavior. We'll use the same DC motor model from the previous video and gradually adjust the parameters to understand their role. Okay, let's start by opening the previous Simulink motor DC motor PID SLX. Okay, as you can see, we have a step input, a sum block for calculating error, and PID controller, and again they represent the motor constants and integrator for the motor dynamic and a scope to visualize the response. This step is perfect for testing how PID tuning affect the output. Okay. First, let's test the system with only proportional control. Set the parameter as P1, I 0, and D 0. Okay, and run the simulation. As you can see, the output start from 0 and smoothly increases toward the target, but it never exactly reaches it. This means there a steady state error. The response is stable and smooth, but not accurate enough. Okay, next, let's add the integral. P1 integral 0.5 and D 0. Okay, and run again. Could start from 0 and rise about 1.2, slightly above the target value, then oscillates before settling value, then oscillation before setting down around 1. Okay, this shows that the steady state error is elemental, but we introduce a bit of overshoot and some small oscillations. The integral term helps the system reach the target, but it also makes it more oscillatory. And finally, let's active the derivative terms to stabilize the system. Set P1, I 0.5, and D 0.01. Okay, and run again. Now the curve is smoother. It rises quickly, has less overshoot, and settle faster. The derivative term helps to dampen the oscillation and improve system stability. So now we have a much cleaner and more stable response. Okay, let's quickly summarize what we saw. Increasing P makes the system response faster but can cause a steady state error. Adding R removes a steady state error but increases overshoot. Adding D reduces oscillation and stabilize the response. Together, these three terms, P, I, and D, form the core of one of the most powerful controllers used in engineering. In real-world applications, PID parameters are tuned using tools like the PID tuner in MATLAB or by analytical method. But understanding their individual effect, like we did here, is the most important first step. This is a greater foundation for designing control system for DC motor, robots, or any mechanical process. Okay, thanks for watching.